Hi students! Alright, this is it. Our last video lecture. And we're going to finish off our last chapter with this last section. And that section is going to be about linear equations and regression. So if you've been following along, we have 2 learning outcomes left. Can you believe it? We had 10 outcomes in the beginning of this chapter. We've done 8 already, after looking at the correlation coefficient, hypothesis testing, and other ways to measure correlation. Our last 2 outcomes today are linear equations and regression. So, let's get started. When it comes to linear equations and regression, we are measuring a linear relationship between 2 variables, specifically using the Pearson correlation. So for the rest of this chapter, when we talk about linear equations and regression, we are talking about linear relationships using the Pearson correlation. The next point talks about a figure 2 slides from now, slide 48, that shows how the relationship works and how the linear regression or the regression line shows the relationship between 2 variables using a line of best fit. This makes more sense when we have the lines. So the regression line itself, we have been looking at scatter plots, points on a graph scattered on the plot, and one way to show the relationship between those 2 variables is to draw a line of best fit that goes through as many of the points as possible, and it will indicate whether the relationship is positive, negative, or none, and how close the points are to that line will show the degree or strength of that relationship. So this line itself, this regression line, makes the relationship easier to see, and it shows the central tendency. And when you see this word, think means here. Again, a mean is a measure of central tendency, and means here would be the math that we use to calculate the regression line. And finally, the regression line here, because it shows the trend of the relationship, we can use it to make predictions. And predictions for correlation between 2 variables for linear relationships, we use the regression line to do so. And the regression line here is a straight line. So to get this line, we need to do something called regression analysis. And it's based on our line formula or equation for a straight line, which includes the slope formula. If you remember this, mx plus b, or some of you might see it as ax plus b. So this is the formula that we're going to start with, and it's the foundation of our regression line. So when we look at graphs for 2 variables, we have some questions that we want to ask before we look at regression lines. Here are some questions that we want to ask. 1. What scale of measurement are we using? Again, you can think back to the different scales. We have nominal, ordinal, interval, and ratio. For purposes of the correlation, Pearson correlation, we're going to focus on interval and ratio scales. The next question would be, well, what type of data are you recording? Is it discrete? Here, think integers, and continuous, think decimals. For interval and ratio, we're going to focus on continuous data, although discrete data is also possible. Finally, we're going to ask the third question, which individuals or participants are we studying? Are we going to study the sample or the population? And again, for the purposes of this course and chapter, we are focusing on the sample. And as we answer these questions, we can figure out or determine which graphs we should use. And the graphs would look familiar to us. And this is the figure B back in 2 slides ago, slide 46, that shows how the regression line makes a linear relationship much easier to see on the scatter plot. Here is the figure, and we see 2 variables here. One, on the x-axis, we have SAT scores, and it's the type of admissions exam. And we have GPA, your grade point average. That's how students perform in schools as they take classes. And here we see a positive linear correlation. So your SAT scores should or would predict how well students do in terms of GPA academically. So the higher a student scores on the SATs, the better they tend to do at college or university. So as you can see here, the points for individuals who in this sample data set that scored low on the SAT, they tend to have a lower GPA as well. It's like over here this much. And then those that scored really well on the SAT, they tend to be, you know, scoring higher in their grades or GPA. And as we look along even sections of these scores, we can see that although the restricted data set looked like cookies, and this is again a caution about restricting X values, but if we look at the data as a whole, you can see that these 4 sections here show the relationship. The better a person does on SAT, the better they do in their GPA. And this regression line here shows that trend. And the line here is a line of best fit, which means the regression line goes through, quote unquote, as many of these points as possible. And another way of looking at this, as we'll discuss later, is that the distance between each point, that is each score, from the same value on the regression line, so the y values for each score compared to the regression line, the deviation score, so to speak, the distance between a y value of the actual score and the y value of the regression line given a point in x, let's say 420, 460, 500, whatever, each point would have the smallest or minimum distance between the y value of the regression line, which will be y hat, and the y values themselves for each score. So these are like x, y's. And if these were ordered, they have x1, y1, etc. This will be x2, y2. This is, let's say this is the 4th one, and so on. So the distance between y and y hat, so here is the data point, and here is the regression line. The regression line is placed where this distance between the data and the regression is the smallest, the minimum value. And we'll explore that more in detail. But for now, that's how the regression line works. It shows the relationship, helps us see it more easily, and it helps us make predictions showing the trend of the correlation between 2 variables. And how we get this regression line comes from the general equation for a line, which you probably have seen before. So this is the equation. Y, a point in y, equals the slope times the x value plus the y-intercept. So a and b are constant. Here b is the slope. Some of you may see this as m in your other classes. A is the y-intercept, which you should remember, given the assumption that you would know this formula for this course in the first place. Now we get to use it. X and Y are the variables. So here's X and here's Y. This point right here, when X is equal to 0, that's your y-intercept. That's your A. And B is that slope. And you're going to see a formula like this. Rise over run. Rise over run. This might bring you back some memories. So you have your slope, that's B. And then you have your A, that's your y-intercept when the value of y when x is equal to 0. Okay. And this is the linear equation for the regression line that we use for this section of the chapter when we look at linear regression. So the regression itself is a way of finding that equation, finding that line, the best fitting line. That is the regression line for a given set of data when the points are plotted on the scattered line. And so this idea of best fitting means that yes, we could draw other lines, including a horizontal line, but that line would, you might think, that's not a best fit at all, because it doesn't hit, like, it could hit like only one point or none of the points. So we want to find a line out of these many possible straight lines. So let's say we have a scatter plot like this. The points are there. So you'd think, oh yeah, it's like connecting the dots, even though you're not necessarily touching the dots, but they're as close as possible. You could draw other lines, like this one, or even this, or hey, let's draw one in the totally opposite direction. But going backwards, this one right here, that's not going to fit, so I'll erase that. This flat one here, that's not going to fit very well, so we can erase that too. This one is sloping upward, but it doesn't fit as well as the line that tries to connect the dots as best we can. And so when we have this best fitting line, what it does for the actual data is that it minimizes prediction errors. That is, this regression line is what we predict the relationship to be. You can think of the regression line as a sort of prediction line that predicts the relationship between two variables or the correlation of those two variables. And this line would have the smallest distance between the y value of the regression line, or quote-unquote prediction line, and the actual y value itself in a given data point. Okay. So we have, let's say here is the actual value, and then here is the regression. This is your y hat. We want these distances to be as small as possible. The perfect regression line would have all the points lined up, and you just draw a line right through those dots, literally. And so the distance between those 2 points would be 0 for each x value. So this would be 0, 1 here, let's call it A, B, C, D, and E. All of these, A is going to have this one, and it's going to be 0. B is going to be 0, and we're talking about the regression line here. This would be a perfect fit. Okay, and these are all y minus y hats. Again, the best fitting line, the regression line, minimizes the prediction errors. That is the distance between y, the data point value, or the y value of that data point, and then the y hat, which is the y value of the regression line at the same x value point. Okay, and so that's what the next slide covers in words. The y hat we've just seen, this is the hat here, we'll just call it y hat for this course, is the value of y predicted at the regression equation. What that means is, for example, if we predict that there's a linear relationship between SAT scores, some sort of admissions test, and the college or university GPA, and we predict it to have a sort of positive, strong positive correlation that as you score better on your SAT, you're going to do better in your GPA, then you would expect the actual data points to be close to, if not touching, the regression line. Some would, let's say do better at the SAT, but perform not as well. Let's say this one right here, for example. Person did better than at the SAT right here. Sorry. Let's try again. So again, this person, let's call this person A and this person B. So person A did better in the SAT. It's closer to the higher score, but scored lower than B when it comes to GPA. So there could be deviations. But when we measure the prediction, measure that point against the prediction line, there is some distance away from that. And that's our next point, y minus y hat. And that's the distance for each data point at a given x value. And x here is going to be your SAT, and GPA is going to be your y. And this distance here has a unique term called the error of prediction. There's going to be one for each point. So let's say if there were 5 people, then there are going to be 5 of these distances that you would measure. If there are 10 scores on the scatter plot, you would have 10 of these that you would measure. And these are errors of prediction. So the regression procedure that is, based on the equation of a line that includes the slope formula, would have a line, and that is the regression line, that makes the square error prediction, and again that's this, and the squared here is y minus y hat squared, and we want to make this value small, minimizing this value, which makes the regression line a line of best fit for all the data points. And this method itself, this procedure that we do, this regression procedure then, is the least, again, think minimum here, squared error, which we just looked at above, squared error solution. And the solution here is the regression line. The solution for finding that line of best fit, finding that regression line that shows us what the correlation between the two variables are. That's the method. The least squared error solution. And this is what that looks like on a scatter plot. Again, we have some x values here. Can name this whatever. We could go back to SATs if we like. And then we have some y values here. Again, we could use GPA here. We predict a positive correlation between those two. And given one of the assumptions of statistics is that people are different, and while we can predict how well or how a person does, people can fall outside of those expectations. It could be higher or lower. So let's say a person didn't do so well on the SAT, but hey, did really well in college. In fact, in the top range even. Right? Whereas we did someone who did really well on the SAT, but still scored, in GPA lower than someone who did really badly, quote unquote, in the SATs. So there is that variability that we account for. But when it comes to regression lines, we are looking at the distance between the y values of each data point and the y value of the regression line. So what I'm drawing here for you are these errors of prediction. we make a prediction about the relationship between two variables. And this is that line of best fit. Again, best fit in terms of fitting our prediction of the correlation between two variables. This is called the regression line. And remember, this line is supposed to minimize or make it as small as possible the squared error of prediction. And you can just say, for concept-wise at least, that we're trying to minimize the error of prediction to the power of 1 or squared. So each of these points here is going to be your distance, y minus y hat. The regression line here has the y hat, not y, because we are using predicted y values, which are not necessarily, and most of the time, are not actual y values. We have actual y values here. y1, x1, y1. Here would be x2, y2. Here's x3, y3. And then this one is x4, y4, and so on. This will be the fifth one. And let's see, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 points. 15 people did this, and there would be 15 of these distances. And this formula here is your regression line. You see, if we draw other lines, let's say here, I draw a line like this. Yes, some points would have, a smaller error of prediction now, but then when you add all these up, it would actually produce a larger squared error prediction because it doesn't fit all the lines as well as the regression line anymore. And especially if we do something like this is obviously wrong. And then you see, oh wow, the regression line is quote-unquote way off. So that's it. And so that's our regression line. That's how it works. So you can try this with your scatter plots in your previous slides. And this is the practice we're going to do to find that regression line using this method. So here we are, the regression equation. So again, there are several equations that we want to use to form the regression line or formulate or calculate the regression line for our last bit of correlation. So here are the equations that you see. The first one is the regression line equation. So here is y hat, and remember these are y hats. These are predicted y values, not the data point y values or actual y values. So when you see regression here, think prediction of the correlation. You got your bx plus a. Here is the slope that we talked about before. Your x is your x value. That's the same for both the predicted y values in the regression line and the actual y values in your data points. And a here is your y-intercept. Here is the y-intercept of the predicted y value, or the y-intercept of the regression line. Okay, so next we need to find the parts of this equation that we need to calculate. That includes b and a. X and y we can plug in, and y hat we can find using the regression line equation. So the first part that we need to figure out is b, the slope of the regression line. Slope of the regression line. So what we need here are the formulas for b and a. Starting with b, we have the slope here is the sum of products, that's your rise, over the sum of squares for your x values. Another way to calculate the slope of the regression line, if we already have the variances and Pearson R, is we have the correlation coefficient, and then we do rise over run again. The variance of your y values, and these are actual data point y values. The variability or variance here, in this case, actually no, this is S, so this is your SD of y values. And then here's your run, which is your variability, your standard deviation of your x values. Again, remember, S squared is your variance, S is your standard deviation. And notice here we're using small s and we're using the English letter R, so this is for sample data. So again, rise over run. We need to calculate the slope of the line first. Next, we also need to calculate the y-intercept of the regression line. So the line goes through a certain point. Here is the mean of x and the mean of y. And we also want to find out the predicted y value, or the value of y hat, when x is equal to 0, which is your A, your y-intercept. Here we have the mean of y, which we can figure out with our actual data. The slope, which we use the sum of products and your sum of squares, x, to figure out. Or if we have your Pearson R, your correlation coefficient, then we need the R and your standard deviations for y and x. And then we also need the mean value of your x values. So there you go. Your regression line equation, starting with the linear equation itself, y hat equals bx plus a right here. And then we need to figure out our slope, which is rise over run. It's based on the idea. Either your sum of products divided by your sum of squares x, or if we have correlation coefficients to work with, then we can use R, the correlation coefficient, along with your standard deviation for y, your rise, over your standard deviation for x, your run. And finally, your y-intercept of the regression line, we need means to do so. So the formula itself is derived from the linear equation. And so to calculate A, we need the mean of y, because the regression line goes through that point. So for example, if we have a perfect one here, the line, then there's a mathematical middle between x and y. And the regression line goes through that point no matter what. And then we have this point here. That's your mean of x and mean of y. And as we draw the line using the equation, there's a point here when x is 0, and we need to find out what the y hat value is when x is equal to 0. So that's your quote unquote A here. And this point is your y-intercept of your regression line. And so with algebra, we can find the y-intercept using the linear equation and plug in some x and y values. Here we know for sure that the regression line always goes through the mean of x and the mean of y. So we plug in mean of x for your x here, and we plug in your mean of y as your y hat. When we know these values, and we do from our data, and we know what the mean of x is, and we know what the mean of y is, and once we figure out what the slope is, using sum of squares and the sum of products, then we can figure out the y-intercept and complete our linear equation for your regression line. That's the first step. Again, based on linear equations that we already know, including your slope formula and your y-intercept. So here is the picture form of that regression line formula, the equations we use. Again, we have our data points here, 1, 2, 3, 4, 5, 6, 7, 8. So with these points, we can calculate the mean of x and the mean of y. That's what we need for A. And with each of these scores, we can find the sum of products and your sum of squares. So for example, your first point here, this is A. So that's 1 and 4, 0 and 2. B, C is 3 and 5. D here is 4 and, oh, if we would go from smallest to largest, that's this way, I guess. So here we got 4 and 5. E is 4 and 6. F is 5 and 10. 5 and 10. G is 6 and 15. And H is 7 and 11. So with these, we can calculate the mean, and we've done that already. Mean of X is 4 and the mean of Y is 7. From these, we can calculate our sum of squares X and sum of squares Y. And we have enough values to do so. We know N here is 8. There are 8 people. And with which we can also calculate the sum of products, which we can refer to in your previous slides in this chapter. And then we have everything we need. We can even calculate R if we wanted to. We have enough there to do these things. So we can even do standard deviations for X and Y. So we actually have all of these. And use this chart to try. You can pause this video right now, copy down these values, or get these values yourself if you're reading the slides, and calculate the regression line using the formula. It's good practice. So the next thing we want to do is see whether the regression line, quote unquote, works. And because we are working with sample data, we have sample error. And if we want to see whether that sample data and the regression line of that sample data predicts the correlation of the population, we need to account for something called the standard error, in this case, standard error of estimate. Remember, the regression equation and the line from which we have the regression line makes a prediction about the correlation, about the relationship between two variables, X and Y, whatever those are. Okay. And so we want to check the precision of this, how precise of this estimate is, because we're working with sample data and we're estimating the population. And we account for this by measuring the standard error of estimate. Standard error of estimate. So this EOE here, EOE, that's your error of estimate. Right here, standard error. And this is based on the standard error formula, which we have your sum of squares over the degrees of freedom. Here, the sum of squares specifically is the sum of squares residual. And residual here, it's related to error. Think of this as error. And you can see that right here. Remember, you have your error of estimate or error of prediction. And so we can set this the formula here. So you got your y hat. This is your predicted y value, which you have before. And this is your quote-unquote actual y value in your data point. And we squared that. Square error of estimate, which we know before, which here, because we already have the words standard error of estimate. You can call this your sum of squares error of estimate, but error or prediction, but we call it in one word, error of prediction. And here, your degrees of freedom, remember, because we are looking at two variables, we're measuring the same people, but we measure them twice, two variables. The degrees of freedom here is n, the sample size, minus 2. So for us to test the prediction, or how precise that prediction is, we need to measure the standard error of estimate. Again, it's based on the standard error formula, which we have done before in our independent samples t-test, in our ANOVA test, and now we do the same with our regression line. So here's what it would look like in a scatter plot and a graph. Here we have, a sample of 8 pairs, scores, or x and y's. And here we have one that's perfect fit. So all the lines line up along the regression line. The line literally goes right through them. Great. Here's one that on the other side, you have points that fall outside of our predicted values. You've seen this before in our figure B. And so we can calculate our regression line and form the line of best fit with the minimum squared error of predictions with these. And we can also estimate the error of estimate, or the standard error of estimate, when we work with sample data like this. This is what it will look like on a scatter plot. Again, both of these scatter plots have regression lines. So even for perfect relationships or perfectly linear relationships, you can still have a regression line going right through it. Or for weaker relationships, the regression line would become the line of best fit. So here are some characteristics of this error of estimate in relation to the correlation between two variables. As R, the correlation coefficient goes up, increases in magnitude from 0 to 1, so the stronger the correlation, the quote-unquote weaker, the less your standard error of estimate is. Your prediction is more precise. You have less error. Remember, your EOE, or standard error of estimate here, is error of estimate. If your data shows a stronger correlation, stronger linear correlation, then your prediction's quote-unquote spot on or close to that, and so you have less error. We can predict the variability of this, and we assume that most of the time there is some error of estimate, which is why we're calculating it. We can make this prediction using a concept we already know, variability. We can predict the variability in y-scores. So here we have your sum of squares regression. And we use regression here because it's the regression line and we can predict it. So that's the regression line variability that is predicted. And here we also account for your unpredicted variability. And this should bring back ANOVA, where we have treatment effect. So this might think back to your treatment effect. And this is sort of your individual differences or randomized differences. But because we're talking about regression and correlation, the predicted value here is the regression, and the stuff that we didn't predict, the variability that is not on the regression line that shows up on the actual data values, those are your residuals. And so we need your coefficient of determination. Here you got your r squared this time, not r, and we multiply that by your sum of squares y, which we have. That's our predicted variability. That's our sum of squares regression. And r here is that correlation coefficient, and we use r squared because we are looking at variability. We need to look at the coefficient of determination, not just the correlation coefficient. And so what's not that, and notice here it's, remember, your r squared is a percentage of shared variability between the two variables. And this is what we predict. This is our prediction. This is our prediction of how the variables correlate or how they change, what their variability is in relation to each other, the shared variability of x and y. I'll use the and symbol here, so not adding them. So because it's a percentage, it's a probability of sorts, and it's a proportion, what's not predicted is that 1 minus r squared. And this brings us back to probability. So we have two outcomes. Predicted variability, that's one outcome. And so in a sense, your r squared here is your probability of that predicted variability. In one sense, at least. And so, because there's only two, there's a variability that you predict and the variability that you did not predict, unpredicted. Then your 1 minus r squared then is your unpredicted variability. And looking at the proportion of this, then we can use it to calculate our standard error estimate and complete our regression lecture. Okay. So the sum of squares y is the same. But for unpredicted variability, we use 1 minus r squared, the rest of the outcomes. And so based on r, our standard error of estimate based on r then is your unpredicted variability, your residual here, which is sum of squares y, over the degrees of freedom. We do not use our regression variability, not the predicted ones, but here is your unpredicted variability. That's your residual, that's your error. Okay, and then that's over your degrees of freedom right there. And we square root that to get standard error. Again, we're not looking for variance, we're looking for standard error, which is the standard deviation of our theoretical distribution. Well, in this case, our prediction of our estimate of the regression line. So with this method, we can test whether the regression line makes a good, quote-unquote, good prediction, whether that regression line is significant. That's what that means. Is that line a good fit? Does that line, predict the relationship between the two variables? Again, the better the fit that line has, the more points that regression line fits through, the more, quote-unquote, likely, the more significant that result would be. So when we analyze regression, that's what we're looking for. And this might be different from what you think. Looking at the null hypothesis here, we can explain this. So the null hypothesis says here, the regression line is 0. That means no correlation. We predict, and remember the regression line is the prediction of the correlation. So we predict the correlation is 0. And this might, remind you of what we had with our hypothesis testing for correlation in the first place. That, oh yeah, the null hypothesis means no difference, or in this case, no correlation. So when we test for regression significance, we predict for the null hypothesis that the regression line is 0, a flat line. The alternative hypothesis then, for at least a non-directional one, the regression line is not 0. It could be positive or negative slope. Again, we use ANOVA here, or similar to ANOVA when we analyze regression. We use the F ratio, which we have used for ANOVA, looking at two mean square values. In this case is mean squares regression and mean squares residual, which we have started working on. And each of these, then we can get a mean squares from our sum of squares divided by your degrees of freedom. So your analysis of regression is indeed similar to your analysis of variance in both concept and practice. In concept, we're looking at how two variables covary, and we're also looking at, in practice, square values, sum of squares values, and then mean squares values, what you get from your sum of squares divided by your degrees of freedom. And also in terms of a hypothesis, yeah, your null would be this no regression line, or rather the regression line is 0, flat. The slope of 0 means the line is flat, signifying no correlation or predicting no correlation. And then your alternative would be, oh, the regression line is not 0. It could be that for non-directional tests, or if you put directions, then it would be either greater than or less than 0, saying a positive or negative slope correlation, or negative and positive slope in the regression line. So we have mean squares and the F ratio which we can get. Again, we have already worked out your sum of squares regression, and we know your degrees of freedom for regression and residual is your n-2. And so the bit that we want to watch out for is how we calculate your sum of squares regression and your sum of squares residual. And once we've done so, then we can divide each one, respectively, your sum of squares regression with your degrees of freedom regression to get mean squares regression, the numerator of our F ratio to analyze regression, and then we can also get your mean squares residual, from which we use our sum of squares residual divided by our degrees of freedom residual to get mean squares residual, our denominator for our analysis of regression. And we use the same F ratio to do this, and we use the same F table to set our critical values, and we use the same steps as ANOVA and the same steps for an hypothesis testing to make our analysis of regression to see if there's a significant regression or regression significance. So going back here, if you're stuck on your sum of squares regression, you can go back to your previous slide, slide 57 here. Your sum of squares regression, again, that's your predicted variability of y-scores. You need your r-squared for this, which you can calculate with your data. You get r, square that value, you get your r-squared, coefficient of determination. Same thing, you get your 1 minus r-squared, which you need r-squared first. 1 minus that would give you your unpredicted variability when you multiply 1 minus r-squared in brackets with your sum of squares y, which you need for both of these. So that's your sum of squares regression and your sum of squares residual, and your degrees of freedom is the same for regression or residual, n-2. So just like we can partition sum of squares and degrees of freedom in ANOVA, we can also partition the same or the similar sum of squares here for regression and residual. Residual here, think error. And regression here, think prediction. For ANOVA, analysis of variance, we think treatment effect. Okay, so for ANOVA, your sum of squares regression would be the sum of squares treatment, quote unquote, or sum of squares between. Right? Here, think treatment. Here, the quote-unquote treatment is our prediction, and for regression analysis or analysis of regression, the sum of squares for our predicted values would be sum of squares regression, because regression here is our prediction. The residual, what's left over, that's our error. So this is another slide, the slide right next to it, for us to use the right values. Again, your coefficient of determination, your r-squared, multiply that by your sum of squares y to get your sum of squares regression. And then your residual, you need your 1 minus r-squared, the remaining probability of outcomes, or the probability of your remaining outcome, which is your non-predicted values, and multiply that by your sum of squares to get your sum of squares residual. Okay. So just the correction here. Your sum of squares residual is your n-2 because we're accounting for individual differences. Your degrees of freedom total is your n-1 because that's everybody. And what's left over then is your degrees of freedom regression. So you might notice here, your 1 plus n-2 would equal to n-1. So the same concept for degrees of freedom in ANOVA, the components, your regression degrees of freedom and your residual degrees of freedom, add those together, you would get your degrees of freedom total. Here, the total is y. It's n minus 1. That's everybody. Okay, so make sure we get this straight, both me and you, that your degrees of freedom regression is just 1. Because that's our predicted value. It's just 1. And our degrees of freedom residual, well, because we're working with individual y values that is on the data set, that's everybody minus 2. So add these up, degrees of freedom regression and degrees of freedom residual, you'd get your degrees of freedom total, or in this case, degrees of freedom y. So that's that. So again, your degrees of freedom regression is 1, is not the same as your degrees of freedom residual. When you add up your degrees of freedom regression with the degrees of freedom residual, you get degrees of freedom y, n minus 1. So that's it for our regression part of the lecture. And we have 2 learning checks. So completing these learning checks would help us then, complete the last 4 questions in our practice sheet. So question 5. We have a linear regression here. We know some values already in the equation. So B, the slope of the regression line is 3, and A, the y-intercept of the regression line is 4. So thinking back to our regression line equation, what is the predicted y value, y hat, for x when x is equal to 7? You can take a moment, write down the equation for your regression line and see what values you can get. Bx plus a. So if b is 3 and x is 7 plus a, we know the y-intercept is 4, so your y hat here is 21 plus 4, that's 25. So we can determine this, and the answer is 25 once we plug in the values of a regression line. So this would be a quick concept check question that you might get on your multiple choice. Again, doing more of these questions like that would help us prepare for our practice questions on your Canvas, whether it's on the practice sheet or in your additional links, that you can start calculating regression lines and testing for significance in our regressions. Okay, 2 questions. That's true and false. True or false, not true and false. A, it's possible for the regression equation to place none of the actual data points on the regression line. True or false? Next, B, if R, the correlation coefficient, is 0.58, the linear regression equation predicts about 1/3 of the variance of the y-scores, or in the y-scores. Take a moment. You can go back to your slides to see, if for A, whether it's possible that none of your data points touch the regression line, the line of best fit, and for B, figure out R and its relation to R squared, and figure out whether, hey, a linear regression equation when R is equal to 0.58, whether that actually predicts about 1/3 of the variance in the y values. So let's take a look at the first question. Is it possible that the regression line from which we get the regression equation from, of which that we can draw from the regression equation, that the line itself doesn't touch any of the data points in the regression line on your scatter plot? And it's possible. Yes, you can have perfect fit, and that's great, where all the points touch the regression line, but your regression line is a line of best fit, so you can have points that don't touch the regression line, and the line would still show the trend. It would still make the prediction. It would still show the correlation and the strength and magnitude if you start calculating the distances between your predicted y values against your actual y values. So yes, it is possible. And 2, or B, yeah, remember the relationship between the correlation coefficient R and R squared. So when we square R, we get the coefficient of determination. So when we square our correlation coefficient, remember the correlation coefficient itself is not a probability, is not a proportion or percentage, but once we square it, we get the coefficient of determination, which is what we use for predicted y, so which we need for our sum of squares regression and sum of squares residual. And when we square 0.58, you get close to 1/3. It's actually about 3.33 recurring. So when we square R, we get the coefficient of determination, which does show, well, how much the regression line predicts the variance. So that's that bit there. Again, once you have major calculations, that is your Pearson correlation, that's your R, you can test whether there is a correlation between two variables. And yes, you can do this with software like SPSS or websites that can do this. But throughout the course and in this lecture, we showed you how the math works, how you can do that yourself with simple data, at least. We can also calculate regression lines, and we can also test or analyze the regression and see if the regression is significant. And it's similar to how we do ANOVA. So instead of analyzing variance, we now analyze regression. And you can try this with a scatter plot like this one, 5 values, 5 points, 5 people, and there's going to get like 5 sets of x and y values. And then we also get a regression line to work with. So that's it. Those are our 10 learning outcomes for our last bit of this course, our last chapter, correlation and regression. One thing I like to say at the end, just to make sure that our degrees of freedom regression is not the same as our degrees of freedom residual. Again, when you add up your degrees of freedom regression with the degrees of freedom residual, you get your degrees of freedom for y. Degrees of freedom for regression is 1. Degrees of freedom residual is n minus 2. Add them together, you get the degrees of freedom y, which is n minus 1. So be careful there, they're not the same. So for this whole lecture, for chapter 14, we have covered all 10 learning outcomes. We have described the Pearson R as a measure of relationship between two variables. We have computed your Pearson R using both formulas, definition and computational. We'll focus on the computational formula. We have interpreted Pearson R and explained its assumptions and limitations. We have tested the hypothesis of a population correlation. Here's rho, the Greek letter rho, not eta. And we do this with our sample R. We have explained and explored the concept of a partial correlation when we include like a third factor and control for this. You can think back to your church and crime weight and include and control for the city size or number of people. We have explored the Spearman correlation coefficient, which will be covered in your test when we use ranked data, and we can use this to test nonlinear relationships, including curvilinear relationships, and we can solve that by ranking the scores instead of working with the interval or ratio scale of the scores themselves. We have explored other types of data, other scales, and what correlation coefficients we use. That is biserial for two different groups measuring the same variable, or your phi coefficient when we measure two dichotomous variables. It could be yes, no, pass, fail, and so on. Here again, it's compute. We explain or compute the linear regression using our regression equation to predict y values, and then we tested the significance of our regression equation, whether we can have a non-zero slope regression for predicting the relationship between two variables. So that's it. That's our course. That's chapter 14. Again, if you have any questions, you can email me on my college email, or message me on Canvas, or leave a comment in the YouTube video if you watched through this. Again, we're here to help you out as you prepare for your final exam in this course. And again, feel free to ask any questions, work with each other, work on your practice sheets. You can do all the questions now, 15 to 18. And yep, keep going, finish strong, you can do this, and we'll see you next time.